right, looks like up and running again. All right, trying to finish the term here, tackling those last concepts. I thought I was done with the Vimes revolution related rates, but we got to do some work with geometric accumulation here, reading graphs, trying to develop a keener sense of the integrative process. Integrative. I guess I said that all right. All right, so let's talk about a rate function, 10 miles per hour. Okay, grandma's on Route 91, traveling at 10 miles an hour, and we know that's why we study math, right? Got to go rescue grandma. We're going to treat 0 as a time. We'll consider it right now, 0. We're going to establish moving into the future, looking back at the past. Grandma's been on Route 91 all term. We haven't been able to rescue her. We haven't been able to get her off Route 91. Maybe before the end of the term, we can do it. All right, so if she's traveling at 10 miles an hour, this gives us a moment in time that we're measuring from, as in right now. Well, where will she be an hour from now? If she's at the Vermont-Massachusetts border, because that gives us our position. X of 0, position at time 0, at right now. Where is she? We're going to say she's at the Massachusetts-Vermont border, traveling at 10 miles per hour. That's a positive rate. And in this case, it's actual derivative of x of t. All right, so we can think of this as the derivative of what's going to become our function, in this case, 10t. All right, and if you travel 1 hour times 10 miles per hour, hours cancel, she just went 10 miles. And if she traveled for 2 hours, I guess she goes another 10, and she's 20 miles north of the border, somewhere around Brattleboro, heading north on that straight 91 all the way up to Canada, about 180 miles north of the border. So then the question is, where was she an hour ago? Well, I think on the next test, you should break these things up. Rectangles, and just go from left to right, 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 so on and so forth. Fill in your geometric shapes, recognize where you're measuring from. So it looks like she's got something that's always increasing. If it's always increasing, then this had to be a number less than that, if she's always traveling at 10 miles per hour north. So if we're measuring from here, then obviously these have to be negatives. So when we're looking above the curve to the right, positive accumulation. Above the curve when measuring back in time, it's negative. Because this is a function that's always going up. Which means that if she's at the Vermont-Mass border right here, then an hour ago, she was in Massachusetts, Vermont, negative mile markers, positive mile markers. All right, so I suggest, as we do the next several, that you just get the geometric magnitudes, figure out where you're measuring from, and then remember widths, sign change. The widths, time is going in the positive direction. Now you're working in the negative direction. That's going to give you a sign change. So let's see. Look at my eraser here. So let's look at what would happen. What would happen if we were measuring from, not from 0, but from an hour from now? 1 hour from now. We're going to measure grandma's movement from that hour. Well, that means that when t is 1, t is 1, let's see, we'll keep that 1. She's at the border right now. She's at the border because we're measuring from here. Well, I think this is going to differ by a constant. I think we're going to get the same shape. I mean, we're still going to get a linear function, still going to be a 10t, but now I think it's going to be, well, let's do it out and find out. So we've got to 1. Oh, that's 10t minus 10 times 1. Yeah, it does look like it's 10 miles difference in terms of where she is on Route 91. If we say that at 1 o'clock she's at the border, well, I think that gives us a little different perspective on the plus c, because now when we go to 2, we've got it in 10 miles. We go to 3, we add another 10 miles. 3, 30, 20, yes. This does look like 10t minus 10. This one looks like 10t. Okay, so let's cut to the chase. Now, keep in mind that the derivative, x prime of t, is equal to 1 times, drop it in, and if you drop it in, it's a 10. There's no variable. Doesn't matter what t is. It's not the best one to give you an example of. Minus the derivative of 0. 1 is 0, so we don't have to do the second half. So, you know, grandma's velocity is 10 miles an hour. Changes a lot if I start doing something like that. It's not just the graph that's the derivative, but we're not going to do that. We're not going to do that. We're going to keep it pretty basic here for tomorrow in class and for test on Tuesday. So let's set one up now. Let's set one up and let's see how we do with it. See if we can answer some questions here. All right, so let's define our rate function. Now let's see. We want to define, we'll call this graph little f. All right, let's go with a big G of x is equal to the integral from, let's start from 1. Now let's go to sub x value on the following graph, ft dt. Dummy variables here. Okay, and this is going to be the graph of f. All right, so let's see what we can get. Let's get grandma off Route 91, and then we'll put her back on Route 91. And we'll create a table of values. All right, so let's see. We need to get Route 91 on here. Now that's not Route 91, that's her velocity meter. All right, so let's see. We'll put her on Route 91, and then let's make that 1, let's make that 2, let's make that 3, let's make that -1, let's make that -2, let's make that -3. Hopefully, it doesn't look like the best scale, but we're going to work with it. All right, so we'll start with 4 here. We'll start here at -4, -2, that's this coordinate. Let's go right up to there, then let's bank to there, then let's go to there, and then let's cut down to here, and we'll end up at +4, -2. All right, we can see that's 3, 0, we can see that's 2, 1, and we can see, let's try to do a little better job here. 2, 1, and this is plain sight. You can see that as well. All right, so I think we're up and running. So I'm going to give you some table values in a minute. Is that what I wanted to say? So we're measuring from 1. So you go put in your numbers. See if you remember what I said about 5 minutes ago as to how to proceed. And you pause the video and do that. And so I'm going to tell you what I basically said before. So I'll put the -4 and the -3 here now that I've kind of butchered that. So that's a triangle, that's 2 units, 2 units, 4, so that's a 2. This is 2 and 1, cut in half is 1. This is a rectangle, 1 times 1, that's 1. And then we got another rectangle, 1 times 1 is 1, that's a half. And that's going to be 1 times -2, so that's 1. Now, what did I say? I did it from left to right, just the magnitude. But now I'm measuring from here. So that's positive, that's positive. Okay, this has to be negative. And going to the right is positive, means that's negative, and that's going to be positive. That's going to stay the same. Okay, so I've got some ability here, I think, to find some values. So what do I ask? I ask things like, what is g of x when x is 4? Well, I think we got it in front of us. 1 and negative 1 cancel. I guess it's a half. I probably should practice. Let's see, I might ask negative 4. I could ask negative 3, but I probably wouldn't. Probably ask 0, on all of those connecting places. 1, 2, 3 certainly is important, and 4. Okay, so those are the important places. Okay, so what would I ask? Obviously, everything hinges on your understanding that when x is 1, her position is the Vermont mass border. That's where she is. 1 o'clock, an hour from now, however we want to think about that. She is positioned right at the Vermont mass border. What is she doing at that instant? Well, derivative's positive, right? So she's heading north. Now, how do we know the derivative is positive? Well, your justifications. Not going to say it is or the derivative is. You have to spell it out. And only one person, I think, really, well, a couple of people. Still haven't corrected C block. But in B block, I saw just a little movement towards what I had stated several times in class, and I'm stating again now. You need to make the connection that little g of x is equal to, applying the fundamental theorem, the derivative of x, which is 1, drop it in. G of x is equal to f of x. On those justifications, you have to make that statement. And I know she's heading north because f of x is greater than 0. That's it. Got to make some kind of comment like that. And about concavity and about increasing and decreasing, things like that. So, all right, so what do we got? Let's do g of negative 4. G of negative 4. Okay, I'm going in this direction from 1. I know what that is. I know that's 0, so I'm going to look at minus 1, minus 2, minus 2 plus 2, 0. How about g of negative 2? Oh, minus 1, negative 2. G of 0, minus 1. G of 2, positive 1. G of 3, 1.5. G of 4, 1.5 minus 1, a half. So what was she doing? Looks like she was heading south. Oh yeah, her velocities are negative from negative 4 to 2. Negative 2 to negative 1. Well, then she's heading north. Oh yes. Velocities from negative 2 to 3. Everything should be going up from negative 2 to 3. Negative 2 to 3. Yes, yes, for mile markers. At north, Grandma. What did she do at 3? Well, velocity 0. It was positive, then it's negative. Looks like we got ourselves a change of direction. Oh yeah, it's all matching up. It's all matching up. Now what happens if all of a sudden, instead of measuring from 1, we measure from negative 1? Oh no, let's make it negative 2. I don't want to be on this video too long. Negative 2. Oh, okay, well, let's go back to everything we said before. Okay, oh, to the right. Above is a positive. Above is a positive. Positive, positive. Below, negative. Oh, these things differ. I think this is going to differ by a constant from the last analysis. And we're looking to the left, right? And above would be negative. So below, got to be positive. Looking from the right, below is negative. Looking from to the left is a sign change, right? As I move to the right, time's moving in the future. As I consider this, looking to the past, sign change. Okay, so now we could add up all these things again. Still going to have the same, where's it increasing, where's it decreasing, concave up. None of that's going to change. But where she is on Route 91 is going to change. That's all about the plus C. Well, in this case, there's no plus C because this becomes big F of t from -2 to x. And so that function becomes big F of x minus a big G, excuse me. Well, no, it's going to change into G in a moment. So big F of x minus big F of -2. And that's what we're calling big G of x. Did I get everything in? Yeah, you can see all of that. All right. And so I think we can see this now. F of x, G of x. I think we can see that connection again from the, the integrative process. All right. So where are we measuring from? Measuring from -2. Okay. So from -2 to -2, -2 to negative. No timing lapses. She's at the border. 0, mile north of the border. 1 o'clock, another mile north of the border. 3 o'clock. What the heck? Where did I go? -2 is 0. Oh, I skipped -1. 0. So we're going here, right? So up 1. Yes, that's right. And at 1 o'clock, I went up another 1. Yes. 2 o'clock. Oh, God. Waking up here. So 1, 2, 3. 1, 2, 3. Guess I'm here. Yeah. Okay. And at 3 o'clock, there's a half. And then I'm down 1 from there. So 2.5. I think I did that right. I feel like I'm too close to a messy board. And 2 here. So she was 2 miles north of the border, traveling at 4 miles an hour. We got to get her off. Traveling at 2 miles per hour south. Oh, yes. 2 miles an hour south. With a decreasing velocity. She went 2 miles south in 2 hours. All right. And so we can see our y values decreasing. And then from here to here, increasing. Why are they increasing? Because f of x is the derivative of big G of x. So f of x equals G of x, and f of x is greater than 0. Okay? What other questions do we ask here? Hopefully that gives you a little feel for the accumulation process, but we also ask questions about concavity. What a messy graph right now. So let's get that cleaned up a little bit. Let's see if that might help. All right. So what are some of the things that I might ask? I might say, well, when is this graph concave up? When is big G of x, not this graph, when is big G of x concave up? Big G of x is concave up when grandma is accelerating. Well, where's she accelerating? Any place on that curve that has a tangent to this graph, that's positive. Okay, well, that's from here to here and right there. Okay, that's going to be a concave up interval from -4 to 0. Why? Because f of x equals G of x, little f of x equals G of x, and f prime of x also equals, well, I think all we have to do is say f of x is increasing. I could go to the second derivative, but that would take more writing. And so because f of x equals, because little f of x equals little G of x, and of course, writing that on a piece of paper, you can see that, and f of x is increasing. Well, that's going to get you a point on the justification. Okay. Tangent line. How would I write a tangent to G? So let's write a tangent, equational line tangent to G of x at x equals, why don't we do 4? Okay, we're measuring from -2. So that was 1, 1, 1, 1/2, -1. I think I got that right. So we know where she is. 1, 2, 3, 3.5, -1, 2.5. So at 4 hours from now, she is 2.5 miles north of the Vermont Mass border, traveling at what speed? not speed, velocity. Speed and direction, -2. Okay, and that's right equation of a tangent line. You got to do the accumulation. You got to be able to recognize that F, this is the graph of F, which is big G prime, right? And that's what you need to write the equation of a tangent line to big G. And the only other questions I ask are about F, about what? G. We ask G, little g, and G prime. So what does G prime represent? The acceleration. And that's all about the rate at which the velocity is changing. So if I wanted to look here, at what rate is that function changing right there? It's undefined. Can't do it at a cusp. If I wanted to know at -3, what is the acceleration at -3? You'd have to look at the slope of this linear section over 2, down 2. So that's going up at a 1-to-1 rate right there. So what is G prime? What is G prime of, what was it, -3? 1. Okay. So those kinds of questions coming your way. We're going to try to practice them tomorrow. I'm going to make a worksheet up. It's going to be on it. Related rates problem, a couple of them, a couple of volumes of revolution, and one of these. That's probably all the time we're going to have. So I'm not going to talk. I'm just going to hand it out to you and say, I hope you saw the videos. And if you didn't, sorry, term's coming to an end. Okay. So math help tomorrow night. This test coming your way again on Tuesday. And then Thursday, going back to the part 1 test. Okay, I'll end this and go correct some tests, make some worksheets. All right.